Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
What's about the L infinity norm? Well, let's look at a point and its projection in the image. And let's introduce some notations as well. Capital U for the scene point and small u for the image point. Then what we want to do is we want to calculate distances in the image. And we measure some point and we have a reprojected point. And we want to look at that residual. We want that to be as small as possible. So we do this for all our image points. We put it in a big vector. And then we put a norm on the vector and we minimize it. And the standard way of doing that is to put use the L2 norm here. And this turns out to be a nonlinear problem with lots of local minima. So that's a part of optimization. So the topic of this talk is to study what happens when we replace the L2 norm with the L infinity norm. This is still a nonlinear problem. But as we should see there, it will be a little bit simpler. But still, we recall that the unknowns can be cameras, they can be scene points, and sometimes the scene points are known, sometimes the cameras are known, etc. So we'll be able to solve a class of geometric reconstruction problem. So the topic is reconstruction with L infinity, but I'll just go through some other recent work I'm doing in San Diego with other people. So these three topics. So the first one is surface reconstruction. So, and please feel free to retract and take your time. So these will be very brief. So I'm interested in surface reconstruction. So we're sort of in the process of developing a feature-based approach to surface reconstruction. So you sort of take your images and reconstruct cameras, and you reconstruct your features. And once you have your 3D features in space, you want to fit a surface with them. And the features may be points, curves, silhouettes, or anything. So what we currently have a paper on this regard is on how do you do this and obeying the visibility constraints. Because often you sort of fit 3D surface to your points and ignoring the visibility constraints. So what are the visibility constraints? Well, in simplest form is that between the camera center and the 3D point, you should, on the visual rating, you shouldn't fit the surface. And so this becomes a constraint optimization problem. So, and one of the reasons for using this information is to get the correct topology of the surface. And here's just a simple illustration. If you only have 3 points and try to fit the surface with those 3 points, you might end up with a wrong topology and use the correct topology. And completely different topic when you're interested in computing camera motion. Sort of state of the art in real-time structural motion is computing these minimal sets and use these minimal sets for ransack in order to get rid of outliers. So I know David Mister will be here next week, so you'll probably hear more about this. This is joint work with David Mister and Frederick Shepleski and Hendrik Stevenius. So we have looked at another minimal case, which doesn't assume full calibration. So we allow for an unknown. The unknown is the focal length, the calibration. So currently there are sort of 2 popular algorithms. One is the 5-point algorithm, which assumes fully calibrated and the other one is the 7-point, which assumes no calibration. So this is sort of a middle way in between using 6-point. So, and one can show one gets 15 solutions in general, and one can compute these solutions very efficiently. And that's the important thing here, because you can compute a solution in less than a millisecond. So you can use it for comparison. All right, so that's all I want to say on that.
6 points. Is this a minimum, or is it 5 and some fraction of points?
No, it's exactly. So 5 points is minimal for fully calibrated, and here then we sort of add one unknown, which is the common focal length. So then we need an extra point to solve for that.
Right.
All right. So when you're in San Diego and working with David Friedman, you must work with photometric stereo. That's one of his big interests. So we've looked at uncalibrated photometric stereo, where you have a setup with a fixed camera and you have a point light source which you move around. And this point light source, you don't know the position of it. You just know you have a bunch of images with varying light. The traditional way of solving this problem is to assume no interreflections. So an interreflection is that each point on the surface here is a light source for all the other surface points. So if you don't assume any interreflection, it's well known that there is a bar leaf and in the solution. So the surface you reconstruct is unknown up to the scaling. It's an affine ambiguity in the surface you get. So and the main result here we have here is if you assume a model with interreflections, it's possible to get unique reconstruction. So you can resolve the bar leaf, and when you have a lot of interreflection, your model is more accurate. Those are two things you get. While the disadvantage is that it's much more complicated to optimize. All right, so let's return to the sort of topic of this one, L-infinity optimization. Here's a brief overview. I'll start with some motivation, why it's useful to, why it's an interesting problem. Then I'll introduce the framework or the necessary machinery for doing this optimization. And then we'll look at some geometric reconstruction problems, triangulations, estimation, predicting transformation and projections, and problems with multiple cameras. And so that this is not a new idea using L-infinity form, and the person sort of most related work is by Hortensia. Let's see. And I think this work is more general. It's been generalized in several directions. What they did is the main result is, I think, that they look at the triangulation case and they show that there is only one local minimum for that problem using the L-infinity, and hence it must be the global. And they also looked at a little bit of the multiple view geometry case. But I think the most important generalization is on the practical side. I would advise I can compute these solutions very efficiently. I think that's perhaps the most important. Okay, so why use the L-infinity model? So what are the alternatives? One alternative is to use algebraic methods. Another is to use the standard L2 method. And the third, if you look at here, is L-infinity. So the algebraic methods, they are usually you rewrite the problem as a linear problem, and you can solve it with SVP. But the problem is that you sort of optimize on meaningless cost function. You don't know exactly what you're optimizing. With L2 method, you do optimize the correct thing, but it's a non-linear, non-convex problem, so there are a lot of local minimums. So with L infinity, you still have a geometrical mean for cost function. That is, you minimize distances in the image. And as we shall see, we're able to get locally optimal solutions with respect to this. So, I mean, the disadvantage here is I haven't proved that. No more spacing. Well, anyway, the disadvantage of using the L infinity node is, of course, that it's sensitive to noise. In some sense, you're sort of optimizing the outliers of the noisiest data. So that's the problem. So I'm assuming that we don't have outliers here. But on the other hand, these other two methods, L2 methods and L-graph methods, they are also known to be sensitive to outliers. So, I mean, we're basically not solving this problem here. So outliers is, I assume, no outliers.
So are you going to tell us practically how one deals with outliers? In other words, under what conditions these are interesting things to study if there are outliers?
Yes, I've studied them under sort of how much noise they can handle.
Mm-hmm.
And I'll give some sort of practical instructions at the end.
Okay.
How they compare to these using L2. So let's look at convex optimization. So let fi here be some scalar value convex function. So assume you know what a convex function is. And if we have some objective function here, f naught, that we want to minimize, subject to a bunch of convex constraints. That's a standard convex optimization problem. And there are efficient software packages that can solve this. So this can be a nonlinear problem. It doesn't have to be a linear problem. So really it's not often here like this is a nonlinear problem, so it's hard to solve, but it should really be it's a non-convex problem, then it's hard to solve. And if it's a convex problem, then it's rather easy to solve. So the generalization of convex is something called a quasi-convex function. Quasi-convex function is if its sub-level sets are convex sets. So what's a sub-level set? You take a scalar, and so that's a threshold for your function. And then you look at all the x in the domain of this function, which is below the threshold. And if this is a convex set, then your function is a quasi-convex. So here's an example of a quasi-convex function. So this function is not convex, but it is quasi-convex. And it follows easily that all convex functions are quasi-convex functions, not the other way around. So why is this quasi-convex? So let's look at one sublevel set. Pick a threshold, 0.6. And you look at all the x in the domain of this set. So this set is the following interval, and an interval on the real line, that's a convex set. So in the one-dimensional case here, if all the sub-level sets are intervals, then it's a quasi-convex function. So here's some properties of quasi-convex function. If we have a collection of quasi-convex functions, F1 to F, then the max of that function with respect to I is a quasi-convex function. And if we have three affine function, that is linear quasi-constant, and if we take the ratio of these squared functions here, and we look at the domain where f3 is positive, and that is also quasi-convex function. And that will be used later. So quasi-convex, how do we optimize quasi-convex function? Well, if we're giving a threshold some value, gamma, and we look at this problem, then this is a convex optimization problem, but it has no objective function. So for a given value, we can solve this feasibility problem. We can sort of find out, is there a solution below this threshold? If there is a solution, we can sort of lower the threshold, and if not, we can increase the threshold. This gives us a way, this sort of leads to an algorithm. Suppose we know that the optimal value of our objective function is in some interval, and we are setting some tolerance and so on. Then we can solve this problem by pick a point in the interval, for example the midpoint, solve the convex feasibility problem. If there is a feasible solution, then we can increase, then we can lower the upper bound, otherwise we have to increase the lower bound. And we do that through the intervals, smaller bound. So this is quite fast, sort of half the interval each iteration. Okay, and the convex constraints that we will be interested in is so-called second order cone constraints. And when you have second order cone constraints, they are called second order cone programs. So cone constraints is one of the following where you have an affine function and you take the norm of that, that's the usual delta, and that should be less than some fine scalar value function. So these cone programs include linear programming, but they are less general than semi-definite programs. But it's not a good idea to use semi-definite program to solve it, because there are specialized programs for second order cone programs, which are not more efficient than semi-definite. And the reason they are called cones, of course, is they look like cones in 3D, so this is just an example. So it's a positive cone. Alright, so that was convex optimization. Let's look at the simplest problem, the triangulation problem. Before we actually attack that, let's look at how we model a camera. A perspective camera using homogeneous coordinates is possible to write as a matrix equation like this, where U here in the image is homogeneous point coordinates, and capital U in the scene is homogeneous point coordinates as well. So what we're interested in measuring the distance, or computing the distance between the measure point and the reproductive point. And it turns out that looking at that equation, the square distance of this becomes, this is the measured x coordinate over here, and this is the measured y coordinate. And it becomes a ratio of these two linear functions. And then you square it. So then, rewriting this a little bit, it becomes something which we have seen before. It's a ratio between square line functions and linear functions. And lambda here corresponds to depth, so lambda is this measure. Alright. So let's look at the triangulation problem. The triangulation problem, the cameras assumed to be known. And we're given matched point coordinates in different images. And we want to find points that match these as close as possible. And generally the array starting sets, so we have those measurements. So how do we formalize this? Well, using the L infinity or the maximum here, we want to find the minimum of the maximum deviation of these three together. And as we have seen, the distance between the measured point and the reproductive point is a ratio like this. And here, the unknown is u. So that this is unknown, so that's the x parameterized homogeneous coordinates. And in this case, f1, f2, and the lambdas are linear functions. So we know that this is quasi-convex, this function. And then we also know that the square root of this is also quasi-convex taking the max norm, the max of all these is also a quasi-convex function. So the whole of this is a quasi-convex function. So let's just rewrite this. Look at the residual gamma, positive gamma here, and this can be, if you multiply up the denominator up here, you can rewrite this in the following form. And this is a constraint. And this gamma here, it actually means pixels. So we have a unit for this gamma as well. And reformulating the problem using these observations, we have this form. We want to minimize gamma such that some constraints are fulfilled. But this is here on the right hand side we have a bilinear constraint, so it's non-linear. So we can solve it directly, but given a gamma, we can solve. So supposing we're, let's say, putting 5 pixels, then we can solve the feasibility problem to test if we have a solution for a given number of pixels. And that's how the bisection works. So let me give you a graphical illustration of this. All right. So triangulation previews. So we're given point coordinates, and we want to find the intersecting point in space. So these cone constraints, well, they actually mean from this free space. So we want to find, so given 5 pixels, let's say that, we want to solve the convex feasibility problem. Does it have an intersection? Yes, clearly in this case it has an intersection. So then we can lower the threshold. We can try with smaller radius of the cones. So let's say 2 pixels. And in this case, there is a common intersection of 3 cones. Not so easy to see, but there is one. And then we sort of lower the threshold again, say 1 pixel. And here we see that they have no common intersection. So then we sort of know that it's between 1 and 2 pixels that we have all. Right, so that was the triangulation. Okay, let's have a look at some other geometric reconstruction problems. Suppose we're giving 3D points in space on the plane and corresponding image points. And we know, without any noise, that there should be a homography that maps corresponding space points to image points. So here, U is some homogeneous plane coordinates. So what would the L-affinity optimization problem look like? Well, we want to minimize the maximum deviation here. But now the unknown is the homography, so it's 9 unknowns, modular scales. Here, and capital U are now supposed to be known. And it's exactly the same form as before. So it turns out that this is also possible. So we can solve it exactly the same way. But now it's a higher dimension. Alright, so this was the simplest projective classification. If you can solve for homographies from scene to the image, you can solve for inter-image homographies. You can solve for projective transformation in any dimension. And replacing this homography with a projection matrix instead, you solve the camera resection problem and projections for any dimension, Dn to Pn is possible.
The condition lambda x is greater than 0. So,
yes, I mean, so that's sort of we assume this oriented projective geometry in some sense. Yes. So that's its limitation if you're in projective triangulation.
but it applies in the case where you're looking at a plane with 2 cameras or anything like that. It's fine, right? Or Yes, that would be fine. Or from a rotating camera, you'd be able to do it, I think. But I'm not quite sure what it would mean in projected transformations of higher dimensions.
No, I mean, that's why maybe this extension is not so interesting.
And camera resection, of course, means the points in front of the camera.
Right. So let's look at some other problems that we can solve the same problem. Suppose we have cameras with no rotation. And again, the corresponding input. Looking at the camera input P, and we have consists of a rotation part, which can be encoded by a 3x3 matrix, and the translational part, which is basically the camera center. And that's the unknown part. And the 3D points are also unknown, so they can be parameters by x2, which is a 3 vector, plus the 1 for making it extended coordinates. Then the projection, p times q, is a linear function again. So, since this is a linear function up here, the unknown, the squared image residual becomes this quasi-convex function. So now we can solve for 3D points and camera translation, as long as we have the rotational parts. And the rotational part can be given by some other sensor, perhaps some other method, or maybe we know it's translating.
Sorry, what about the condition there that lambda is greater than 0?
Oh, that's no problem. I mean, we're in the situation where we assume that things are in front of the camera. That's sort of basic assumption. So you would have to know the sign of these rotation pieces. Here again, using a reference plane. Suppose we're given a reference plane, and we know that some points in C lie on a reference plane, plus some other points. Then, as we've seen, then we can compute inter-image homographies using the elements. And then knowing these inter-image homographies is basically equivalent to knowing the rotational part of the camera. So, using the inter-image homographies, we can go back to the previous model and solve that instead. So then we can find the cameras and the 3D points for any number of views, as long as we have the inter-image homographies.
I guess that's not entirely obvious to me, right? I mean, it seemed obvious, but then I thought maybe I have a doubt. Once again, with respect to this condition about lambda greater than 0, because it's as if that plane happens to be the plane at infinity, right? Then it is exactly as if it were rotation, but it's not the plane at infinity, and hence the question of what points are in front of the camera and what points are not is a little bit.
Yes. I mean, there are situations where there are some limitations to it when the camera sort of sees a limited set of these points and some points happens to be that of the camera.
Well, also the other points. I mean, you're going to be optimizing over all the other points, not only the points on the plane, right?
Yes.
And if that plane happens to be the plane of infinity, then you've got a ready condition which tells you that the points are in front of the camera, right? And that's, well, effectively you're in a Euclidean, but this is not a Euclidean. You're not talking about Euclidean reconstruction here, are you? So you're talking about projective reconstruction of the plane. And so I just wonder if there's an issue there with the usual thing of what's in front of a projected camera and what's not, and hence that what is the boundary region in space that you use? Just not a problem. You've implemented it and it works.
It works, and yes, I mean, there are some things in that. you have to be careful how you compute these models. So just make sure that points are proper again.
Right.
The lambda constraint, which is the plurality that says it must be in front of a certain plane, right?
Yes.
That's just one row out of the
Right.
matrix. So as long as that denominator has points in the right direction, the forward-looking direction, you're okay. So you sort of have to get the sign right. You don't really have to get the plane at infinity. Any reference plane works.
Well,
but you
as
have
long
to make
as
sure
it's
that
beyond
the
all
last
points, yes.
Does it have to be beyond all the points?
Sorry?
Does it have to be behind all the points, the other points?
No,
I
I'm
was
not
under
saying
that
reference
kind
plane. I'm not saying the reference plane had to be, but the plane of where lambda equals where
Yes,
the x
lambda-
lambda equals 0 has to be
Exactly.
beyond.
Lambda is just a linear constraint. It's not a plane.
Yes,
Well,
exactly. So
it's a vector.
in this case, there is a coordinate freedom. I mean, you have a translation of the world coordinate system, and there is a scaling of the world coordinate system. So, and this, you can set this be such that at least one part is going to come positive, and then the others should as well.
All right.
So that's a normalization of the world coordinate systems. Make work. Alright, so I've tested this on some real sequences to check how it works. This is just an example. And the algorithm using the reference plane algorithm is you track your page points in a sequence. This is a sequence consisting of 36 images. And then you can compute the inter-image multipliers if you know which ones are on a particular plane. In this case, I've chosen some points on the turntable itself, which is a. And then you can use the previous algorithm to calculate the remaining part of the canvas, all the three points. And then you get projected reconstruction. And then you sort of take this frame. And this, I mean, now I have tracking points myself. They're up here, they're called. And then you can illustrate reconstruction. It becomes, it's very accurate. This is just some images from. You can see the cameras, how it is in circular fashion.
How accurately are they a circle in the end?
You see here is the first, this is the last.
Fairly accurate. All right. What have you done for rotations here? You're assuming you know the rotations.
No, I mean they are obtained by inter-image models.
Oh, on the ground plane or something?
Yes,
On the blue plane? Right. Okay.
So given that there are no outliers in the sequence, what's the advantage of using L infinity over L2 in this case?
Oh well, L2, I mean first of all it requires some kind of initializations. And one way to get initializations is to order effect.
Right, because you can, this idea of using homographies, right, this is plane plus parallax, about 10 years old at this point now, right? So, but you can estimate the homographies using L2 instead of L infinity. And what's the advantage?
Oh, let's see. I mean, the way to estimate L2 homographies is to use some kind of method for initialization.
Right.
And then you do the normally.
Oh, okay, I see.
Refinement.
Division.
I mean,
Okay.
the L2 is subject to, a local minimum, right?
I mean,
Is the problem, and you're dependent upon you.
so there's no closed form L2 solution.
There is the improperly scaled direct linear transform, right, the algebraic
Yes,
solution.
the algebraic. I mean, so this
Which
is
is not
sort of
optimal,
competing
right?
with the algebraic method.
Right.
Yeah. So the algebraic method sort of has no well-defined cost function, but this one has a well-defined cost function.
It's well defined, but which one's closer to the gold standard, as you would call it in your book?
Well, I think that's clear. The algebraic one can be has no relation, whereas this is as close as L infinity norm is to L2 norm, which is close.
Okay.
Right.
Okay, I think I'm starting to see why.
Right. I mean, if, for instance, you get an error of 5 pixels from this method,
Yeah,
you know for sure there's something
We'll
wrong.
get back to the question. I'll give some examples of, I mean, I'll compare it to
Okay.
the standard DOT.
Okay.
So here's just, if you have the quotient in the substitute, right here. So let's look at it. So here's all the image residuals for the L infinity. So these are, I mean, X and Y residuals in the images. So typically what you see here is that the tails of the distribution are much wider when you optimize the L2. So the L2 optimization has been obtained by applying bundle adjustment to the solution obtained with the L2. Then you see that with the L2 it's sort of gets more peaked naturally.
So I don't understand how the residuals can be bigger in the L infinity, because aren't you minimizing the maximum residual?
Yes, but these are residuals. I mean, image residuals.
Yes.
So they are measured X and Y coordinates wise. So they are measured with the L2, the image, right?
Right.
So the max.
No, I don't quite follow. I mean, the L infinity norm is minimizing the maximum residual, so how can
Yes,
it
but
have
there is
longer
some
tails?
residual out here which is larger.
I see. Okay, I thought you said the L infinity had longer tails. That can't be the case then.
Okay, no, okay. What I meant was that there are more points out here compared to this. Like, the distribution gets more peak from 0 to M2.
Right.
And I mean the linear algorithms or algorithm, they have been around for some time. So they are quite good, so it's hard to beat. And here's just an example. I tried to do triangulation. When I get my solution, I can sort of try to do triangulation. And sometimes, yeah, if you measure with the L infinity, that's of course but it beats the other one. That's just the way of checking that my implementation is correct. But if you use the root mean square arrow, which is the L2 one, then the linear algorithm is sometimes better, and sometimes the L infinity is better with respect to the L2 form. And you can do this with synthetic data, and you sort of get the same behavior there. Sometimes the linear algorithm is better, and sometimes the L infinity is better. So it's not. But then it's a question. I mean, what's the right way of measuring how good an algorithm is? Is it the root mean square error? Or, I mean, somehow it's if it converges to the statistical optimal that we optimize it further. That's the right way of judging things. But there are also, I mean, the linear algorithm can be way off. So that really doesn't have to do with the energy as long as you don't have outliers. Here's just some implementation info. The one I've done is based on the SOCP, which is a public available software package. And the running times, solving one feasibility problem, for example, for previews, triangulation is 50 milliseconds. Solving this dinosaurs sequence with 36 images, 328 points, with over 2,200 tokens takes about a second. And typically, one only needs 5 to 10 iterations to reach the optimum in order to sort of get an info which has a range 10 to the power of 25. And it's even possible to improve on the bisection method to do better than half the So, in conclusion is, so I presented a L infinity framework for unit reconstruction problem. what you get are a globally optimal solution with respect to the homogeneity model. And the solutions are invariant to the coordinate system. So I sort of like this image here. So we have the L2 method, the algebraic method, and the L-infinity model. And so my conclusion is that the algebraic methods are, there's really no reason for using them. With the L-infinity model, you have a guarantee that you get a global optimum and you optimize something that is geometrically unique.
Well, for the cases with the L-infinity norm is appropriate, right?
Yeah.
What do you mean appropriate?
Well, so like in a central matrix, right? Unknown rotation. Is that a case where this would work?
Okay.
Well, will work is what you mean.
What's that?
When you say appropriate, you
would
mean
be
will
defined.
work.
Yes.
Oh, will be defined, I think, as reasonable.
Yeah, okay. So the conclusions I'm drawing here are the sort of problems which are quasi-convex. I mean, otherwise it's
Right,
hard
right.
to do the optimization. These conclusions don't hold if they are not quasi-convex. But I mean, there is a class of problems which are quasi-convex. For this class, I don't think our break methods is there's no reason to use that.
Other than simplicity.
Well, simplicity. I mean, it's quite simple to use L-infinity.
Yeah. Well, if you have Sadumi and MATLAB, it's
Okay,
quite
you
easy.
have convex optimization tools. I mean,
Yeah.
linear methods are easy if you have an SVD. So,
I mean, yes. I mean, I basically agree that algebraic methods are not to be trusted at all. Right. If you,
So what, I asked a question about, or someone earlier about outliers, and you said you'd talk about real data, but this was clean data that was tracked by hand, so there were no outliers.
oh, well, let's see. I think this data is tracked automatically, but the outliers
Have been
cleaned
removed.
out.
Yeah, no, okay,
So-
that's what that's correct.
Right.
So what I'm saying, what I meant was that it works for normal noise levels. Fine. And the outliers have been removed.
Okay.
So,
So
and I think, I mean, this method can be devised to use for outlier removal.
Uh-huh.
I mean, because if you set a fixed threshold and you get a solution, then you know that you have a valid solution. Whereas with an algebraic method, if you use that for outlier reduction, if you don't get sort of a valid solution, then you don't know if it's due to an outlier or it's due to the method itself. It's the same with you don't. I mean, if you get a bad solution, you don't know if it's bad due to that you're stuck in a local minima or it's bad due to there is alpha is no good.
So you would propose using this in ransack for, say, point triangulation?
Well, it depends. I mean, I mean, it's not as fast as solving these input sets, which you do in real-time structural motion.
Right.
So it uses very fast solvers. So it's not as fast as that.
I think that I mean, on an early slide you had there's a comment which I sort of objected to, which was saying, okay, the L2 is statistically optimal. My question is, statistically optimal, why do we not use it? Why does no one actually use it? If you're really serious, you use some sort of Huber distance, or you remove basically real-world problems. And even if you do give outliers, they're not L2 norm. There's no way.
Well,
there's no way.
That's the best modeling assumption we have.
Right. Well, I'm not sure. I mean, it is a modeling assumption, right? And I think
Yeah,
I think the only reason people use it is because linear least squares is closed form, and there are all these good methods.
Okay, yeah.
Right. So I think that, and all the other stuff about saying, well, this is therefore the maximum likelihood because we're assuming Gaussian noise, is really sort of, justification after the fact. That's my belief. You argue for these methods it's sort of like in self-justification, but they're not really. It's not really the case that Gaussian noise is what you get in the image, right? and therefore these are not maximum likelihood using L2.
Well, no one has measured most of them.
No, I mean, you can develop one for a particular problem. You can look at the log,
Yeah, I mean,
the
I'm not,
histogram of the noise.
So
Yes.
a couple of slides ago, said it's not clear that the root mean square error is the correct way of judging these.
Right.
So if you don't want to use this inside a RANSAC loop, then you said it's better to just use a minimal solution technique, and then.
Well, if you compare to speed.
So you would use a minimal solution to hypothesize, to propose a particular motion.
Yes.
Then you would see which points are consistent, which are inliers based on that, and then you would use the L infinity. I'm trying to get a sense of how one would use this in this
Yes,
rotating
which is
system.
effectively what you do with L2 in any case, right?
Yeah.
You use trifocal, and Zisserman, for instance, and Fitzgibbon, they use trifocal tensor method of getting rid of 3 views, get rid of outliers using sets of 3 views, and then use that, and then just do bundle adjustment on the, with Berman the belief now you've got a reasonable set of data.
So,
Okay.
I've tried this on relatively clean real data, but the L infinity solution is really close to the L2 solution. That's what I thought. If you sort of do bundle adjustment for that, you get 2 steps.
So there's this additional issue with algebraic methods and the L2 norm of, you have these minimal solutions for, some subset of the variable, right? So like two cameras on a sequence, right? You can do an algebraic method or a minimal solution, do ransack, and you find some set of inliers between the two, only considering that. You do this for some number of pairs, and you come up with an initialization that's probably sequentially generated, right? But you could just do all these pairs and not worry about the sequential initialization problem, throw it into an L infinity norm, and as long as you didn't have outliers that were still there, right, it would give you the built solutions. Right? But, so the question is, how many outliers do you still have in that case? So you have to have some sequential initialization that is weeding out additional outliers when you throw in the additional constraints that all these cameras and points are seeing the same scene.
Well, I suppose if you apply this L infinity to the data that you think you got rid of all the outliers, and you still got residual 10
Does it actually tell you the outlier, right? So it gives you a solution where, so it doesn't tell you the outlier, though, right?
Well,
If the solution you get is, the optimal is 10 pixels, and then there is some point which gives this 10 pixels, then it's quite likely that that's the outlier.
yes. I mean, obviously the point with the outlier has to be one of the points which are firm up against you. If you've got 1 million points, you solve these things, there'll only be a smallish number of those which actually satisfy the constraint, right? And you know your outlier must be one of those. So you certainly have, right, but beyond that.
So I guess it's my intuition, but I'm not convinced that is it actually?
Well, yes, because if it's not up against your constraint, it might as well not be there, and hence the effect of it's an outlier is irrelevant. Right?
Okay, so then in this case you would optimize the L infinity norm, look at your points that are up against the constraint, and start throwing them out, and iterate that way.
Yeah, well, we all know that with L2 that's a bit of a fishy technique, right? But it's a possibility. Well, another thing, actually, with this rotation and translation problem, right? I mean, the complete motion. There's not a unique solution, not a unique L infinity solution here, right? Actually, so because those points which are not constrained can actually move a bit, right? Probably is the reason why your thing of residuals is spread. Yes. Spread over. Is that going to be a problem? I don't know.
Thanks for your talk.
So there, in that dinosaur, there are enough points on the ground for you to actually get a ground plane.
Well, in that particular case, I had to add a few points so I could get the integration from all these to one reference.
Right.
I did that by adding a few points.
Yes. But I'm still a bit worried about that, because I mean, in this particular case, of course, the ground is behind all the other points, right? And hence.
Oh, well, I mean, I'll use it on other sequences. I'll try to get
Yeah.
other sequences as well.
I'll just have to look at that a little bit to understand it. But I think as a way of doing long sequences, instead of this thing of having to build up bits by bit, which is drift. You've got a way, get your rotations first, and just throw it in here, and you'll get the solution without having to initialize straight up. I mean, I don't know how this would scale to
Well,
a couple of thousand images or something like that.
but for estimating homographies, right? It works, right? You said you.
Well, homography is a bit different. Well,
Well,
no,
so
no.
there's still a problem, right? So
Well,
if
what
you have a
about-
long sequence with a lot of images
Yes.
in a homography, you know, you're trying to estimate homographies between all of them.
Oh,
Yes.
you wouldn't have, I mean, you could estimate sort of the two-view geometry somehow and get the rotation between consecutive two views.
But that's the
well,
sequential initialization issue, right?
what if you got correspondences of points on it? Is this a problem which is amenable to it? A set of points on a ground plane, a set of points on a plane, correspondences, but not sequential. I mean, so for instance, take a photo mosaic, and you've got correspondences between pairs of images all over the place, right?
Yes.
And you want to get all the homographies at once, the optimal set of homographies. That I'm not sure whether this is a problem which would yield to this quasi-convex approach.
No, I don't think so, because you sort of assume that the noise is in one image. It's not a symmetrical error function.
Right.
So,
Yeah. Well, that's not quite clear. Well, yes, maybe. Okay. Thanks.